begin the third lecture. So yesterday, in lecture 2, I explained mostly the material. It's a classic material about 3D n equal 2 series. So that was about, I would say, that the series in the 90s. Well, of course, we live in the 21st century. So why not go to the more recent stuff? And there are a lot of substantial progress in the field of supersymmetric gauge theory recently, and then I'm going to utilize all these developments. And then the developments are partly technical and partly conceptual. And the conceptual thing is the thing I tried to explain in the first lecture, where we have new ways of thinking about quantum field theory. But that's only one aspect of the story. And another story is that we have new techniques, powerful quantitative techniques to analyze supersymmetric gauge theories. So that's 2000. Well, it's hard to say precisely, but say 2009 and on. There are a lot of techniques, and that goes by the name localization computation. So that's a tool. And with this tool in mind, I'm going to explain the connection to three-dimensional manifold, as promised. So in fact, this is a little bit ambitious plan because I think I could almost give a 3-hour lecture just about 2D localization. But I try to be minimal, and also try to explain the three-manifold case in such a way that the connection to the first lecture is clear. So let's start with this localization business. Well, so what's the deal? So we have a class of 3D n equal 2 series, 3D n equal 2 series. And yesterday I discussed its vacuum moduli space, for example. What are the properties? There's the Coulomb branch, Higgs branch, quantum corrections, etc., dualities between them. So that's a beautiful story. But in physics, it's quite often useful to extract something more concrete, namely numbers or functions which depend on some parameters. And the useful quantity is that you can compute something, some very concrete numbers, like for example, the partition function on S3 or S1 times S2 with a twist. So it's called index, or S3 mod Zn. So it's a length space, or the factorized version, etc. There are a lot of partition functions we can compute. So what I mean is that, right, so what I mean by this. So first of all, I start with the 3D n equal 2 theory, Lagrangian. Well, I try to emphasize Lagrangian is not fundamental, but for doing this computation, the Lagrangian is useful at least. And then if you understand the case with Lagrangian, and then we can try to extrapolate to more non-conventional cases. So let's start with the Lagrangian. And when I have the Lagrangian, what I have is the Lagrangian in flat R3. Now, you can try to put this on the curved manifold. And then there are some cases where this is extremely easy. For example, suppose that this theory is conformal, and you can just do the conformal transformation, and then you put the theory on S3. But in general, if it's not conformal, you have to modify the Lagrangian, and also the supersymmetry transformation. Well, first of all, I'm going to take this to be really S3, Euclidean S3. So I have to do the Euclidean notation. But not only that, I have to change the Lagrangian, and then modify the Lagrangian. So there is term like L1, R squared, L2, etc., etc. And the motivation for putting the theorem S3 is that it has better IR behavior. But there are still UV divergences. So in quantum field theory, there are UV divergences and IR divergences. And there are still UV divergences, which I'm going to regularize after. However, if this is S3, so it's a compact space, so there are no IR issues. In other words, I could compute the partition function R3, but then of course it diverges. So you can think of this S3 as sort of a regularization in a sense. So let's take the radius of this S3 to be R. and that R comes in. And of course, when the radius goes to infinity, we go to the flat space. So it should go back to the original Lagrangian. So that's why I wrote this thing this way. Now, there are problems because there's actually there are infinitely many ways of putting the theory on the Kalam manifold. Because I could try to choose this, etc. So we need some principle. So the principle is I want to put the theory in such a way that at least some of the super. So in this theory, 3D equal 2, we have Q alpha, Q alpha, Q with Q bar alpha. There are 4 supercharges, but such that at least one supercharge, some supercharges. Some supersymmetry is preserved.
Masahito, to regulate the UV divergences, is some regularization preferred over others, or because in the literature I've only seen zeta function regularization being used?
Yeah. Okay. So yeah, I don't know the a priori argument why the zeta function regularization is good. In fact, I don't know the deep reason for that. Yeah. I mean, of course. Right. So I'm going to check that. I mean, to present evidence for the duality, for example, but I can. Between supersymmetric gauge series, but I can turn the argument around that I believe in the duality and use that as a check of the UV regularization, for example. But that's not a good argument. Yes, and there are a lot of consistency checks, and it's easy to convince yourself this is a natural choice. But if you really press me that if it's the only choice, I don't really know, honestly. Yes. Right. So I want to preserve supersymmetry, but quite often. None of the supersymmetries can be preserved. And one way to see that is that you want to write down the Lagrangian. Quite often, well, for example, we need a Killing spinner. We might need a Killing spinner or some similar version. So on S3, so probably I should write it here. On S3, we have some so-called conformal Killing spinner. So please know the conformal Killing spinner. And then there are 2 choices, plus minus. So there are 4 supercharges, but if you pick up one, and then you only pick up only 2 out of the 4. And it's not hard to imagine that there is some restriction on the geometry you can consider. If you have some spinner, a nice spinner, a Killing spinner, or the generalization. Well, first of all, it's called a conformal Killing spinner because you can take a Killing spinner equation and apply the conformal transformation to that. And then you obtain basically this equation. Now, so that's the this, and then so I need to have some nice geometries which have some nice spinners, and that puts some constraint on the possible geometry. But roughly, if you have some spinner like this, you can take a fermion bilinear, and you can construct a Killing vector out of it, which is generates isometry, for example. So there you can try to do the argument very generally, like a generalized geometry, etc. But the point is that if you have some spinners, and then there are severe constraint, but not too severe actually, but some constraint on the possible geometry. And S3 is the simplest one, is satisfied criteria. Now, so in some supersymmetry, so in my case, I'm going to preserve only 2 of the supercharges by taking, say, cross factors. And these epsilons will appear in the supersymmetry transformation. So first of all, not all the supersymmetries can be preserved. And besides, not all the symmetries, not all the symmetries need to be preserved. But at least I want to preserve some supersymmetry. So let's call this supercharge Q. There might be 2 or several. In this case, there are 2. But let's call this supercharge Q. And also, I want some minimal choice. So what people do in the literature is to say, choose this Lagrangian in such a way that all these are 0. So they're just one of R and one of R squared corrections. And that's a non-trivial fact. Well, for example, if you start with the flat space Lagrangian, you can add the so-called conformal coupling to the scalar, for example, and then try a supersymmetric completion. So that's this term, and then try the supersymmetric completion, etc. And then once you add certain term, you have to modify the supersymmetric transformation too. There are one of R corrections to supersymmetric transformation, and you have to go through that, and then try to check if supersymmetry is invariant, supersymmetric closures, etc. That's what you have to do. And well, and that choice, even that choice is not unique. But let's say so, and suppose that we have such a choice, and then I could compute the potential function on S3, which is the path integral of all the fields, and then I mean the Euclidean signature. I have this action integral of the action. So this is and I integrate over the field configuration S3. But then the trick, which goes by the name of the localization, is that you can add the term, which is Q exact. Namely, you take something called V to the action, and this is independent of Q as long as supersymmetry is not spontaneously breaking, because you can take a derivative with respect T. And then, since this is a derivative of the exponential, commutator term comes in. But then you can use the Leibniz rule to act on this. So I mean, this Lagrange itself is invariant under Q. So this one, so you can convince yourself that the derivative of this guy, so it's independent of T. So in particular, I can take a limit where T goes to infinity. And but that so far doesn't help too much, except unless something special happens. And something special means that suppose that this Q exact term is a sum of absolute value squared. There are some expressions inside. And it's not too hard to imagine, for example, what this V should be. Well, to give you a flavor, for example, V could be trace Q lambda, say Q lambda bar lambda, for example. Suppose that I have a gauge field, and then this lambda is a gauge inner, for example. And then this QV is trace Q lambda dagger Q lambda. So this is the same one with its conjugate. So this should be definite. And in fact, in the gauge theory, the supersymmetric transformation for this guy contains a term like F mu nu, gamma mu nu. So this term contains the term like trace F mu nu, X rho sigma, gamma mu nu, gamma rho sigma. And if you do that a little bit of exercise, this contains a term, well, this becomes the term like F mu nu, which is the, well, of course, the kinetic term for the gauge field. But there are also other terms in the you can learn. And there are also one of our corrections, because I have modified this supersymmetric transformation by one of our corrections. So if you have, this is for vector multiplet. So if you have a chiral multiplet, you can take again the fermion, and then write down the similar thing. So this is the explanation why this holds. But suppose that this is absolute value squared, and then if you take the limit t goes to infinity, this expression almost well, maybe I should take minus here. If this goes to infinity, and the whole thing becomes 0, unless this is 0, and the thing inside determines this subtle point configuration. And so this should be 0. So there are various different expressions, but all this should be 0. But that's not the only end of the story, but that's the leading order, the first power in T. But of course, in the limit T goes to infinity, that kills the leading order in T. But there is also a constant term, T to the power 0, in this expression. And that means that the fields could actually fluctuate a little bit away from the saddle point, suppressed by some power of 1 over T. So, in the limit, the path integral localizes to saddle point configurations. And And this is a one-loop fluctuation because there are higher order fluctuations, but these are suppressed. So I took the constant part. So I could only take the leading fluctuation, which is the constant part. This is that. And then there are higher order fluctuations, which is suppressed by 1 over t, 1 over t squared, etc. But these vanish in the limit where t goes to infinity. Which means that all I need is the one-loop fluctuation. So by this logic, it follows that this partition function localizes to saddle point configuration. And then, well, first of all, there is action. So there is action evaluated at the saddle point. So that's the zeroth order term, one of the zeroth order terms. So let's call the Z classical. So classical contribution. And then there are also one loop determinants.
Can you remind me where the information that you apply n equal to 2 went into this argument that you wrote?
Oh, okay. So in fact, n equal to 2 is not strictly speaking necessary. In fact, I mean, right. So far, for the purpose of, I mean, the only thing I need is just I have one supercharge, and also that this is positive definite. That's the only thing I need, right? So in principle, this could work for any theory as long as you have some supercharge. Yes.
So what is special about n equal to 2?
Yeah. So what's special about n equal to 2 is in that, right? So I wrote this as a saddle point, but however, this could be another complex thing. I mean, namely, these are the fields. So that could depend on the coordinate values, like phi x, for example, where x are the coordinates. So this saddle point itself could also depend on might allow some field configurations which depend on the space-time directions. But what's special about 3D n equal 2 is that from this saddle point equation, it follows that only constant configurations are allowed. Right.
But people have studied n equal to 1 theories using localization as well.
Oh yeah, I have thought about that too, in fact. But that there are some subtleties, and it's open question. Yes. And I would say that that's right. So somehow, right. So the special case about 4D n equal 2 and 3D n equal 2, for example, is that this becomes a right. So space time coordinate independent config saddle point. And in some cases you obtain space-time dependent saddle point. But still, that could be useful. And that's the case, for example, if you take I'm reducing a little bit, but say let's take a 4D n equal 4 and on S4, for example, and people could put the various Wilson line, for example, and not the circular Wilson line, but some shape, for example. That's considered by Teston and John Lee. And in that case, that's another general shape of the Wilson root. And they did this localization. And in the end, saddle point configuration was not constant in specific space-time, but allows some fluctuations in two-dimensional direction out of 4 dimensions. So they discovered the connection to 2D and for example. So in that case, 4D computation localized to 2D computation. Here, in this case, 3D computation really localized to 0D matrix model computation. Yes, that's right. So that's a very good point. So in fact, let me write explicitly. So for 3D and so what's the saddle point? So this is a very general argument. And so what's special about 3D n equal 2?
Can I ask another question?
Okay.
You calculating this on the round metric?
Yes. Yeah. That's in fact that's also another thing coming to. In fact. Okay. So I could do that. So So there are a lot of it. And So for example, I could count this in the round metric, or some deformations of that.
You're gonna do that?
Yeah. In fact, that's
okay.
right. So the question is So there's one obvious question. So I mean the space of metrics on S3, that's infinite dimensional space. So do we obtain an infinite family of the partition function? And it turns out that the answer is no. So since you asked me, so let me first mention it. So Z3, so it depends on the so-called integral contact structure. On S3. And the integral contact structure is an odd-dimensional analog of the complex structure. So the complex structure is there is a local function and there is a C2 power n, and the transition functions are holomorphic. So that's almost and that's the same as having the integral complex structure, where the integral almost complex structure, and that's just something switched j which squares the minus 1. And this is the analog of the complex structure of S3. And people have studied this structure in S3. And then there are two, as far as I know, there are two such things. So there's one parameter family. So this is discussed in the paper by Dimitrescu, Festucha, Croce, Komagovsky. And then, well, there's another thing which is a zero. So it's like a point, zero parameter family. And as far as I know, nobody has localized it for this one. So I'm going to concentrate on this one parameter family. So let's call this one parameter B, for example. And one way to say that is that, for example, you can deform the matrix of S3 to be this one equal R squared, but well, say let's take the radius we want. Maybe I should take R squared. Where this B is the deformation. Z and Z2 are complex coordinates. So this, in this deformation, well, SO3 has SO4 symmetry, which is SU2 times SU2, but out of that, only SU1 times U1 is preserved.
So the zero parameter family is not going to be the same.
Yeah, I would expect the answer to be different, but you never know. It might be that the answer happens to be the same, for example.
Or with special value.
Yeah, it could be. I don't exclude the possibility theory. And nobody has, yeah.
You want your partition function to depend on some continuous parameter.
Yeah, that's right. Well, but I mean, maybe even if it doesn't have a continuous parameter, it might be useful for checking the duality. So, but
then it goes back to the question about the UV regularization. It's not obvious what it means to have a partition function with no parameters.
Well, sorry, but it still depends on some parameters, like the mass parameters, which come here.
Some
Right, so-
theory data.
Sorry? Yeah, some theory data, like a chance and zero, for example, or mass parameters and things like that. Right, so strictly speaking, it's not a number,
But
it's
in
a
the
function.
conformal limit, all of that is.
Yeah, that's right. So in that limit, all the mass parameters, of course, etc.
So for the conformal theory, you do need some parameter to make sense of what you're doing.
Yeah, that's right. Yeah, that's right. Yeah.
So is one parameter B similar to the squash sphere cube?
Yeah, so this is sometimes called a squashed sphere, in fact, 3 sphere. So in standard notation, this is called SVB. Although that's maybe I'm digressing too much, but sometimes, for example, this one preserves U1 times U1 symmetry. But in fact, there is another way of putting supersymmetry, supersymmetry 3 identical to series S3, such that it's different from that, but preserves SU2 times U1 symmetry. But nevertheless, it's right to the same answer. So in fact, even though even the amount of symmetry is preserved are different, they might have the same answer, for example. That's related to the fact that only some information out of the whole matrix appears in the S3 partition function.
And still have the two supercharges preserved in this picture?
Okay, so I think if you deform it, I don't remember, but I thought it was one supercharge. Well, for sure, for S3, there are 2 supercharges. Sorry, for round S3, there are 2 supercharges. I don't remember the case with this. Probably one supercharge. Okay.
Sorry, Masahito, very naive question. So the localization can be used for any physical observable that don't have t dependence, right? If I just insert whatever thing in.
Well, I mean, okay, so you can use the localization for any observable consistent with supercharge.
Right.
Right. Because when I used this argument, I took that derivative with 6 to t, this one comes in, etc., and then sort of use the Leibniz rule, etc. So
if I put in any supersymmetric correlation function in there, I can just use.
yeah, exactly, right. So in fact, for example, that's true. And people are especially interested in, say, Wilson loop, Tofu's loop, for example, consists with supersymmetry. So I mean, that should be consistent with this supercharge Q. So that determines there are some constraints on the possible shape of the Wilson line, for example. But then you can compute it.
But like even for vanilla correlation functions, you can also.
Yeah, certainly, yes, that's right. And I should say that this story of localization itself is not at all new. It's known in the 90s, for example, in the 2D MLs, when Witten computed the 2D MLs partition function. He was essentially using that.
Actually, there's some subtlety, like for example, Wilson loop you can calculate by like one Wilson loop.
Yes.
You can calculate, but can you calculate correlation function of Wilson loop?
I think so. Except that sometimes, right. So for localization purposes, you can sometimes put the Wilson line in a particular point, for example. And but I think that's an interesting point. In fact, so you can try to discuss the algebra of loop operators, for example, using this partition function techniques. And there's a paper by Brian and Willett and Kapustin, for example, which indeed does that, for example, and then discuss the connection. It's sort of a 3D lift of the Grassmann, but sorry, I'm digressing too much. So let's see. So sorry, I'm too slow, I guess. All right. So
Okay.
yeah, sure. So that's this right. So Right. And the point is that, so since I don't have much time, let me jump into the precise identity corresponding to the derivative. So the idea is that, well, of course, depending on which theory you take, you have different looking expressions. And I'm going to present you one example for this expression, which comes from this localization. So that example, let me remind you that it's the duality between SQED, one flavor. So let's go, I was calling it Q and Q2 then. And that's related to this X5C model. Now, the identity is the forms. So this is the duality between Q series. So it should be that I could take, evaluate the partition function on both sides. And they should be the same. So this is a precise mathematical identity, and which is why this technique is so nice. I mean, you can talk about field series, moduli space, or homomorphic, etc., but this is just concrete expression. So what's the, how does it look like in this particular example? Well, in this example, it looks like that this one looks like B sigma exponential 2 pi I. I'm going to explain the notation from here. 1 minus R cubed. IQ over 2, 1 minus R2 tilde, minus sigma minus B. And so this expression is IQ over 2, 1 minus Rx, plus minus 2 mu. It's a product of 3 factors. So rather than explain the general rule, I explained this example, and hopefully you can get the general recipe. 1 minus Rz plus mu minus zeta. So there are many things, so let me explain the notation one by one. So first, as I said, there are three things. So there's the integral of a set of points over some parameters. And it turns out that this parameter, integral parameter, is the same as the Coulomb branch parameter. Maybe I didn't introduce the Coulomb branch parameter, but the parameter sigma. Sigma of the Cartan of the vector superfield. So recall that in yesterday, I was saying that this is the same as mu sigma lambda d. And the sigma was the third component scalar. That was a real scalar. So whenever there is a gauge series, so I'm going to do the gauge series computation. So let's take the Cartan. Well, I'm thinking about the abelian theory. So Cartan is nothing but the same as the original gauge group. And I'm going to, there is a parameter associated with that particular vector superfield, and I'm going to integrate it.
Is it always guaranteed you localize on the Coulomb function?
Well, sorry, but let's see. I mean,
Oh, you are basically.
well, in a sense, it's not okay. So I call this a Coulomb branch parameter because this is a parameter parameterizing the Coulomb branch in flat space.
Okay.
However, this is a S3. So in fact, well, people call it a Coulomb branch localization. That's because this is the Coulomb branch parameter. But Coulomb branch on S3 is completely different from the Coulomb branch on flat space, for example. So this is not, strictly speaking, this is not the integral over the Coulomb branch of R3, flat R3.
Right, I guess
It's
the
something.
point is that there could be other, you could localize at other points of moduli space, right?
Mhm,
You could
mhm.
localize for example, Higgs function.
Yeah, that's right. I mean, for example, I mean, this partition function is going to be, well, yeah, that's right. So you can turn on both real mass parameter, Fi parameter, for example, to this partition function. But it's known that the Coulomb branch in flat space, for example, is lifted. If you turn on Fi parameter, for example. But nevertheless, partition function doesn't become zero. So there is exponential decay in fact. So, right. So this is right. So this is something